Hello everyone and welcome back to another video. Today we're going to finish up our chapter on prime numbers by discussing the distribution of primes. And this is one of the more complex, full of unanswered questions, ripe for new discoveries areas of number theory. For some of this we're just going to do a brief overview of what the question is, what the theorem is or conjecture is, without a ton of proofs in this video, because some of these would go deeper and involve more complex number theory that isn't fitting for an introduction to number theory course. But without further ado, let's jump into the discussion. So today we're going to talk about the distribution of primes. And earlier in our chapter, we proved that there are infinitely many primes. But there's still so many other questions that we can ask about primes besides how many there are. Specifically about how primes are distributed among the naturals. For example, what proportion of the naturals are prime numbers? Do primes occur in any sort of pattern? And how wide are the gaps between primes? Now, many of these questions and conjectures along with them are still unanswered or unproven. And those that are answered often have some very complex proofs that's beyond the scope of our course. But in this video, we're going to give a brief overview of some of the more important and famous conjectures throughout history. But we're going to start, like with all these videos, we're going to include a proof of one of the more interesting ones that we actually can prove at this level of introductory number theory. So one thing that we can actually prove at this point in our number theory journey is that we can find arbitrarily long strings of consecutive composite numbers between primes. And this basically means that for any natural number, we can find a gap between two primes where no primes show up of that length. In other words, we can find gaps between two primes of 1,000, 1,000,000, 1,000,000,000. Any natural number that we can come up with, we can find a gap between primes or a string of consecutive composite numbers of that length. So let's jump right into the proof of this theorem. Theorem Theorem 2.46. And this is there exist arbitrarily long strings of consecutive composite numbers. And then in the statement of the theorem, they restate it with a that is, or that is. And this can kind of give us some direction on how we can prove it. Sometimes you'll see, like, within the textbook that we're using, there will be like an initial statement and it'll be that is for blah, blah, blah. And it'll state it in a form that's easier to conceptualize a proof of. So what we're going to see is how we can conceptualize that proof. That is for any natural number n, there is a string of n consecutive composite numbers. And then for our proof of this, what we're going to do is start by simply just defining a natural number n. So we're just going to let n be a natural number. And then the next step that we're going to do is we're going to construct this number x. And x is also a natural. Let x be a natural such that x equals n plus 1 factorial. And there's a very specific reason that you're going to see why we construct x in this particular way, why we make it n plus 1 factorial. Additionally, just because we're going to use this set a lot, I'm going to say this a lot throughout the proof, let A be this set. It's a set of all numbers from 2 all the way to n plus 1. So A, the cardinality of A, which means how many elements are in A, is n. So it goes from 2 to n plus 1. Okay. So now, one thing to note here, A divides x for all A in the set capital A. So for every number in this set, let me scroll down a little bit. For every number in this set, we see that it divides x because x is n plus 1 factorial. So it's just the product of 1 and 2 and 3 all the way to n plus 1. So all of these are factors of x. Thus, since A divides A, just trivially, every number divides itself for all A in A divides x plus A for all, and I'm going to say for all A in A many times throughout this proof, by theorem 1.1. This was actually the first theorem that we proved in this course. It was that if you know that A divides X, I think the way it was stated was if A divides B and A divides C, then A divides the sum of B and C. So that is that. Next step. And then now we know for all of these A's in the set A, 1 is less than A is less than x plus A, because x is always greater than 1 in this case. Wait, is that true? Yes, because if we start with if we start with a natural number as 1, x at minimum is 2. So 1 is always less than A is less than x plus A for all A in A. X plus A is composite for all A in A. And why is that composite? Because A is between 2, is not 1 or x plus A. It's between that, so it has to be composite because it's one of those other numbers. And a composite number is just any number that's divisible by a number other than 1 in itself. And then since the cardinality of A is n, this set of numbers is a set of n. Yeah, because all these are all consecutive numbers. It's x plus 2, x plus 3, x plus 4, all the way to x plus n plus 1. So this is a set of n consecutive, and all of them are composite. Consecutive composite numbers. So basically, what we showed here is that if you pick any number n, we can find a set of n consecutive composited numbers by taking n plus 1 factorial and then adding 2, adding 3, adding 4, all the way to n plus 1, and all of those numbers should be composite. So we have this set of composite numbers of length n. So we know that we can at least find n consecutive composite numbers. So there must be a gap of at least n between those two primes. So there's arbitrarily large gaps between consecutive primes, which gives us some idea of what the distribution is, because we know that there are infinitely large gaps, or arbitrarily long gaps between prime numbers. And one thing you do kind of see, if you were to write out like a list of prime numbers, like at the beginning, the very small natural numbers, like there's all sorts of primes here. But then you start seeing them start getting spaced out a little bit more, like there's that gap of 4, and now we're seeing other gaps of 4. And then as you continue on, there starts being wider and wider gaps between primes. So this ultimately, as we keep going, we end up seeing that any possible length that we want, there is that length of gap between primes, or at least that length of gap between primes. Okay, so this is this shows there's arbitrarily large gaps between primes, but what about the smallest possible gap between two primes? For example, we know that there's primes that differ only by 2. For example, 3 and 5, 11 and 13, 29 and 31, 41 and 43. And then this list continues on and on. These are actually called the twin primes. And then the question now is, does this go on forever? Are there infinitely many twin primes? Now, the answer to this question is IDK. I don't know. We haven't proved it yet, though we have made some progress over the past few decades, but this is still technically an unsolved problem, and this is called the twin primes conjecture. Basically just saying infinitely many twin primes that differ by only 2. So this is still unsolved. However, there has been some progress in this problem in the past couple decades. We actually have found that there are infinitely many pairs of primes that differ that differ by a number less than 246. So we're able to bring it down a little bit, but we're not quite to the point where we can reach 2. So we know something about the gaps, and there being like infinitely many pairs with a certain gap. That's a certain smallness basically, but we've only gotten that bound down to 246. However, apart from this, this is unsolved. So this is an example of an unsolved conjecture. That's not a P, that's a D. And that's a very famous unsolved problem. That would be a good one for you to attempt to solve if you want to change the field of mathematics fundamentally, or solve one of these unanswered problems. Now, along with that, that's talking about gaps between primes. One thing that we also know about is that we actually do have some idea of, is the approximate proportion of primes, like the approximate what proportion of the natural numbers are primes. So to start, there's this function pi of n, and this is basically this is the number of primes less than n. And what we found is that this number of primes less than n is approximately n over ln of n. And actually, as the number gets larger and larger, as n gets larger and larger, this becomes a better and better approximation. And ultimately, what we do find is that if we take the limit as n approaches infinity, of basically the ratio between these two numbers, we find that it actually does equal 1. Now proving this is way beyond the scope of this particular number theory course. Feel free to go look up proofs on your own. They might be a little bit complicated. But yeah, so this is that result basically shows that over the set of all the natural numbers, the infinitely many natural numbers, essentially that is the proportion of them that are prime could be seen as for n would be like 1 over ln n, basically. Actually, that doesn't fully work, but this ratio for larger numbers, as numbers get larger and larger, ultimately, like 1 over ln of n becomes a better and better approximation for the proportion of primes that are less than n. So this becomes a better and better approximation, and that gives us some sort of idea of what proportion of the natural numbers are actually prime numbers. Okay, so with that out of the way, the next thing that we can discuss is one last famous problem regarding the distribution of primes. And we're going to start here just by writing even numbers as the sum of two primes. So we can see, like, even numbers you tend to be able to do this. So 4 equals 2 plus 2. 6 equals 3 plus 3. 8 equals 3 plus 5. 10 equals 5 plus 5. 12 equals 5 plus 7. 14 equals 7 plus 7. And then 16 equals 5 plus 11. 18 equals 7 plus 11. And then 20 equals 7 plus 13. And this continues on and on and on. You'll find if you keep going that this pattern continues. And if you find that it doesn't continue, you should probably tell somebody that because that would be a revolutionary finding. But you'd have to go pretty far to find a number where that pattern doesn't continue. But the thing is, we still don't know if this does continue on and on forever. Is every single even number able to be written as the sum of two primes? And that is Goldbach's conjecture. Goldbach's conjecture is this. And like the twin prime conjecture, this one is also unsolved. But there's also been a lot of work done on this, and there are some things that we do know. We know at least that this is true for most or very close to all of the even numbers. So if there are exceptions, there are very few exceptions relative to how, like, in the grand scheme of things, like in the grand scheme of infinity, that's it could be a lot, but in the overall distribution of even numbers, if there are exceptions, there are relatively few. And we know that every single even number that we have checked holds the Goldbach's conjecture, so we haven't found any exceptions yet. However, we still haven't ruled out the possibility of there being an exception. So it is possible that we keep computing these numbers, we keep finding more and more evens. If we just keep going and going and going, we will just keep keep finding that there are more and more even numbers that can be written as the sum of two primes. The problem is, in the grand scheme of infinity, all the even numbers that we found are basically none. Like, we haven't even dipped our feet into the pool of the infinite number of even numbers. So it's possible that just way out there down the line, there could be some exception. And we haven't proven that there is no exception. But we feel very confident that the Goldbach's conjecture is true, even though it's still, or I personally feel confident that it seems true, even though it hasn't been proven. It's possible that there is an exception. So that's Goldbach's conjecture. That's another example of an unproven theorem about the distribution of primes, or unproven conjecture about the distribution of primes. And with all of that, that is actually everything that I have for this particular video. Compared to some of my other math videos, this one is very short, but we were just kind of, in this video, rather than proving a bunch of things, just kind of concluding our chapter on primes, seeing what there still really is to be discovered and where we can continue making progress in the field of prime numbers, which, as simple as they are, as early as we learned them in our lives, there's still so much complexity and depth here that continues to stump great mathematicians to this day. But there is progress to be made. There are proofs to be had. There's things to still be discovered. So that's one thing that's exciting about almost any field of math. You can go, especially number theory, you can go very deep and find all this complexity, but then there's still these like foundational unsolved problems that have been kind of at the forefront of number theory for centuries, for millennia. Like some of these, a lot of these go back even to Euclid. So yeah, that's the interesting thing about number theory. And I just kind of wanted to end our prime discussion here with some of these unsolved problems, so that after this, in a few weeks, whenever I decide to post the next episode of our introduction to number theory, we're gonna step away from primes, at least for a little bit, and jump deeper into modular arithmetic. And that's chapter 3. We kind of introduced it in chapter 1, gave some foundational some foundational understanding of what modular arithmetic is. But in chapter 3, we're really going to start diving deeper into it, seeing how like polynomial functions work in the modular world, and start diving into that a little bit more. And that chapter is called, it's chapter 3. It's titled A Modular World. And yeah, we're just slowly getting through this book. We finished the first 2 chapters now, which is crazy. And then we still got a lot to go. And some of this was even beyond what I ended up getting to in my number theory course. So we'll see how all of that goes too. I'm going to start learning things at some point in this course, but yeah, so that's all that I have for this video. I hope you guys are enjoying this. Feel free to go down and like and subscribe if you're enjoying this content and want to see more of it. There's also a Patreon down below if you want to support my work, and a Discord as well if you want to discuss or ask questions or find a community. Trying to build that as kind of just a community of viewers basically and subscribers. So that's that, and I hope you all enjoyed this video. I'll be back next week with another video, likely on theology. So kind of interspersing the math and theology videos all throughout my channel. But yeah, it's 2 subjects I really enjoy. So those of you who are of similar mind to me, I hope you guys all enjoy this content. I'll be back next week, and then hopefully another math video within the next month, and then we'll just keep going every week. It's the grind. But yeah, okay. I hope you all enjoyed, and I cannot wait to see you all in the next video. Yeah. Peace.